All right, as I mentioned, our presenter is Dan Hani. He is a director of high performance HVAC solutions at Veritech, and he has a deep expertise in energy efficient design, refrigerant transitions, and advanced systems. Dan works closely with engineering teams and building owners to implement scalable decarbonization strategies across the Southwest. He also is very active in ASHRAE. He is a current distinguished lecturer, and he serves on several committees. He also is an author of several publications in ES Magazine. So Dan, I'll hand it over to you.
Kelly, thank you very much. And thank all of you for joining us today on this presentation, Designing and Controlling VRV Systems with A2L Refrigerants. Before we begin, I have to, I really, an expression of a debt of gratitude to two gentlemen whose hard work over the past for education has given me a lot of the information I was able to build into today's presentation to give today's session a context. One is Ed Mendieta, Western Regional Applicational Engineer for Daikin, and Bill Dietrich, Daikin Applied Director of Chiller Applications. And I want to say, as I'm really not involved in the day-to-day laying out of VRV systems or variable refrigerant systems, I've had the good fortune of talking to Ed Mendieta this week, and he is present at our presentation today. Ed can answer any specific design questions engineers may have regarding A2L refrigerants and variable refrigerant systems. So confident Ed would be happy to step in should we have some questions I can't answer. Today's session is somewhat dense. It's not so much a 20 or 30,000 foot flyover of A2L refrigerants applied to VRV systems or variable refrigerant systems. It's a foundational system, a presentation. It's really looking at the history of A1, A2L refrigerants. And then we're going to do a deep dive into Standard 34. We're going to look at Standard 15. And then we're going to look at designing A2L variable refrigerant systems in conformance to Standard 15. And then we're going to go through a very simple office example to show how to calculate releasable refrigerant charges to space and see if whether or not that space is in compliance to the Standard 15 and the refrigerant concentration levels the standard calls out. Then we're going to look at the language or some of the language in Section 11 of the International Mechanical Code 2024, and then a design suggestion to help mitigate refrigerant volume within a building by using a decoupled 100% outside air variable refrigerant system. And if time permits, perhaps some concluding remarks. So let's look at variable refrigerant systems. What are they? Well, remember, HVAC systems are really fundamentally were invented for thermal comfort in buildings. And to create an environment that is comfortable, you have to remove thermal energy. And thermal energy is comprised of two types of heat loads. The heat load that is actually measured at a thermostat and is felt on the skin as heat, and latent heat, which is the amount of heat energy necessary to keep water in a vapor state. HVAC systems provide the cooling and dehumidification of buildings to maintain thermal comfort by maintaining space set points. Conventional HVAC systems, however, use air as a heat transfer medium. Air is a fluid and it has mass, and so it can carry and convey energy. By injecting a large volume of air at relatively high velocity of 150 feet per minute at diffusers, a mixed air environment conceptually is created. So you have a plus or minus 2 degree temperature variation throughout the cubic volume of space. The problem is, if you use air as a heat transfer medium, it is not very dense. So you need a lot of air and consequently a lot of fan horsepower to move the building's energy. To give you an example, if we look at air as a heat transfer medium, air can carry only 0.46 BTUs per pound of air. So you need a lot of air to move the BTUs necessary to condition a building. If you look at chill water, which is a more dense heat transfer medium, water carries 8.98 BTUs per pound of water. And because water is more dense, it carries a lot more energy with a lot less volume. And this is why chill beam systems and decoupled hydronic systems have become popular high-performance design strategies, because it takes a lot less pumping horsepower to move the sensible energy from a building than it would otherwise require for air. Well, let's look at refrigerant. Refrigerant is even 10 times more dense, arguably, than water. So what if we use refrigerant as the heat transfer medium? And that puts us in the domain of variable refrigerant systems. So what is a variable refrigerant system? What is its technology? Just as a quick review, because we have many different people from various experience levels with HVAC systems in this presentation. Consider variable refrigerant as a demand control refrigerant flow systems. Condensers are remote from fan coil units, unlike your package DX units at home. Fan coil units are located locally at each zone of control, and the condensers modulate refrigerant flow based on demand in each or all of the zones. So refrigerant flow is modulated based on demand, which means the compressors do not work 100% because they're unable. They modulate, and this removal of the on-off start-stop cycling sequence adds a lot of efficiency to a system. Systems are able to ride the heat load in a space. And here's a dynamic graphic illustrating the two types of variable refrigerant systems available. Heat pump systems, where condensers can either be in heating or cooling zone, serving all the independent zones associated with the indoor fan coil units, or they can be in heat recovery mode, where a single condenser can provide a means of simultaneous heating and cooling at each of the fan coils connected to that condenser. So what is an A1 and an A2L refrigerant? Well, let's look at a brief history here of the refrigerants, because I think it's an important awareness to have. Actually, I was surprised to learn that the vapor compression cycle was invented in 1834 by Jacob Perkins. I think he was the first one to actually make a device. It was being worked on a couple of decades before that. And Jacob Perkins used ether as the heat transfer medium in the vapor compression cycle. The problem is that ether is toxic and flammable. In 1859, Fernando Carre came up with an ammonium refrigerant vapor compression chiller. Why ammonia? Because it was more efficient than ether, and it had a lower flammability level as well. Well, obviously, there's a reason why that was considerably popular at the time. However, ether, ammonia, and sulfur dioxide are toxic and flammable, and there was a significant pursuit of a more safe refrigerant, and that refrigerant was discovered or invented by Thomas Midgley of General Motors back in the 1920s. And he used a CFC refrigerant, a chlorofluorocarbon refrigerant. And it became the dominant refrigerant of choice for HVAC systems from the 1930s through the 1970s. R12 Freon is an example of a CFC refrigerant. The CFC challenge is that it's a high ozone depletion. It has a high ozone depletion level. When a CFC refrigerant is released into the atmosphere, in the upper stratosphere, UV light breaks down the CVC into oxygen, O2, and free chlorine gas. Well, free chlorine gas interacts with ozone to create oxygen and, again, free-floating chlorine gas. So it's a self-perpetuating, self-generating process. Consequently, it generates significant amount of greenhouse gas emissions. Oh, I'm sorry, it has a far deeper impact on the ozone levels within the upper atmosphere. And in 1970s, two scientists by the name of Rowland and Molina theorized that CFCs were capable of depleting Earth's ozone layer because of the equation I just spoke to. In 1985, a hole was discovered in Antarctica's ozone layer, and it was significantly worse than scientists had predicted. And in 2 years, 1987, through global action, the global community came up with the Montreal Protocol regulating CFC ozone depletion substances. In 1992, HCFC or hydrochlorofluorocarbons were added because though they have a lower ODL level than CFCs, they still have a high ODL level. Well, the good news is that reading an article and doing research for today's presentation, I found a paper generated by Paul Newman of NASA that states that the gradual improvement we've seen in the past 2 decades of the ozone level or the ozone layers over the Antarctic shows that intentional efforts, curbed ozone destroying chemicals, are actually working. So we're noticing that the ozone levels in the Antarctic are beginning to recover, and a lot of that is due to the strict regulation of CFC and HCFC refrigerants. So when there was a regulation of CFCs and HCFCs, a transition refrigerant was sought after, and that is HFC refrigerants. HFCs were a good bridge from since the initiation of the Montreal Protocol because they have a low ODL level. However, they have a high global warming potential. HFCs are among the most potent greenhouse gases, a global warming potential of greenhouse gases, hundreds to thousands of times more than CO2 in a shorter time. Consequently, because of this pressing need and the acceleration of climate change we're experiencing, HFC phase down occurred through the signing of the Kigali Amendment to the Montreal Protocol in 2016. Why? Why was this move to reduce the GWP caps on refrigerants? Well, ASHRAE's decarbonization site has this rather compelling statement that environmental challenge is compelling because the global building stock is predicted to double by 2060. And there's going to be increased global demand for conditioned buildings. People are tired of living in uncomfortable environments. And the fact is that buildings generate approximately 40% of global greenhouse gas emissions, and the HVAC system generates 40% of that 40%. So there is urgent need, as perceived by ASHRAE, to expand standards to address the impact on climate change due to the result of high global warming potential refrigerants, as well as other decarbonization strategies. Well, in the United States, the American Innovation and Manufacturing Act mandated in December of 2020 that HFCs would be phased out by 85% by 2036, and the phase out was to be managed by the EPA. So which refrigerants have come to take the place of the HFC refrigerants? Well, HFOs, which are hydrofluoroolefin refrigerants. An olefin refrigerant has one carbon-carbon double bond, and double carbon bonded molecules are more unstable than single bonded molecules. HFO refrigerants have zero ODLs or ozone depletion level capability and very low global warming potential ratings. Why? Because fluorine is the halogen component in the molecular structure, not chlorine. And the double carbon bond of an HFO breaks down rapidly at lower levels in the atmosphere, and consequently you don't have free floating chlorine mixing or high GWP molecules being emitted into the upper levels of the atmosphere that are impacting the re-radiation of solar energy that hits the earth throughout the day. So anyway, there's a breakdown of why refrigerants have been transitioning to low ODL and GWP limits. And we're going to look at how those levels are determined by analyzing ASHRAE Standard 34, 2024. First of all, Standard 34 is really created for a way of designating safety classifications of refrigerants. Its purpose is intended to establish a simple means of referring to common refrigerants, and it establishes a uniform system for assigning reference numbers, safety classification, and refrigerant concentration limits. Its scope is to provide unambiguous system for numbering of refrigerants, and it does not imply endorsement or concurrence of any of those refrigerants. It just states each refrigerant's physical qualities. Before we begin with looking into Standard 34, let's make sure we have a common understanding of certain definitions and acronyms. We need to understand what burning velocity is. BV signifies the burning velocity of a refrigerant measured in centimeters per second. We need to understand what the term lower flammability limit means, or LFL. It is the minimum concentration of a substance in a flame can propagate in throughout a homogeneous mixture. So it is the lowest concentration limit that will support a flame throughout the mixture. An understanding of refrigerant concentration limit is necessary. The refrigerant concentration is determined in accordance with this standard, Standard 34, and intended to reduce the risk of acute toxicity, asphyxiation, and flammability hazards in normally occupied spaces. And then an understanding of occupational exposure limits is another term to understand for the standard. It is the time-weighted average concentration for a normal 8-hour workday and a 40-hour work week that all workers would be repeatedly exposed to. So Standard 34 actually took on itself the numbering of refrigerants. The identifying numbers assigned are such that the chemical composition of the compounds can be explicitly determined. The first digit on the right is the number of fluorine atoms in the compound. The second digit on the right is one more than the number of hydrogen atoms. The third digit from the right is one less than the number of carbon atoms. And the fourth digit on the right is equal to the number of unsaturated carbon-to-carbon double bonds in a compound. So if we look at R1234ZE refrigerant, it has 4 fluorine atoms, 2 hydrogen atoms, 3 carbon atoms, and 1 unsaturated carbon bond. And for R32, which is the primary refrigerant for variable refrigerant systems, there are 2 fluorine atoms, 2 hydrogen atoms, and 1 carbon atom that can be discerned by referencing 32, the number 32. Standard 34 also in section 6 provides safety group classifications. So in 6.1.1, the classification of refrigerants, the safety group classification, it states that the safety group classification shall consist of 2 or 3 alphanumeric characters. The first character indicates the toxicity as determined in section 6.1.2, inflammability in section 6.1.3. Under 6.1.2, the toxicity classification is Class A for refrigerants that have an occupational exposure limit of 400 parts per million or greater, and classification B has to do with refrigerants have an OEL of less than 400 parts per million. 6.1.3 assigns flammability classifications. There are 4 classifications. There is type 1, type 2L, type 2, and type 3. So an A2L refrigerant is a refrigerant that has an occupational exposure limit of 400 parts per million or greater, and it is a class 2 for flammability, which is low flammability level. So be aware of that. And the characteristics of each of these refrigerants is listed in figure 19 to the left. I can't read the numbers. It's so small on my slide to reference, so I apologize for that. So if we look more closely at safety group classifications, class 1 refrigerant is a single compound refrigerant that does not show flame propagation when tested in air at 140 degrees Fahrenheit and 14.7 psi at sea level. A class 2L refrigerant has a lower flammability rating. A single compound refrigerant shall be classified as 2L if the refrigerant meets any of these 4 characteristics. Again, flame propagation of 140 degrees, a lower flammability limit of greater than 0.062 pounds per cubic foot, has a heat of combustion of less than 8,169 BTUs per pound, and a maximum burning velocity of 3.9 inches per second or 10 centimeters per second. Section 7 of Standard 34 references refrigerant concentration limits. A single compound refrigerant, like R32, has a concentration limit for each refrigerant shall be, for single compound refrigerants, the refrigerant concentration limit for each of the refrigerants shall be the lowest of the quantities calculated in accordance with the 3 sections shown below: 7.1.1, 7.1.2, 7.1.3. So the lowest assigned value for either of these 3 classifications will assign what that refrigerant classification is. So Standard 34 is very clear about that. So what does Standard 34 language reveal regarding the comparative nature of, let's use 3 refrigerants. Let's use a refrigerant used in variable refrigerant systems, historically R410A. R410A refrigerant is a compound refrigerant of 50% R32 and 50% of R125. It has an occupant exposure limit of 1,000 parts per million per volume, and it has a safety group classification of A1. And in previous editions of Standard 15, the refrigerant concentration limit for an A1 refrigerant, or certainly R410A, was 26 pounds per cubic foot. And because it was non-flammable, it has no flammability rating nor any burning velocity. So 26 pounds of refrigerant per 1,000 cubic feet is quite a bit of refrigerant. If we look at R32, we notice that the occupant exposure limit is the same as R410A for asphyxiation, but it has the safety group listing of A2L for non-toxicity, but for flammability. Consequently, Standard 34 assigns 4.8 pounds of refrigerant per 1,000 cubic feet of room volume. So it's substantially less than the 410A listings. And the lower flammability limit, which will be used to determine effective dispersal volume charges for refrigerants and VRV systems, is now a factor. And if you look at the burning velocity of R32, it is at 6.7 CFM per second. If we look at the refrigerant our manufacturer is using for their chillers, R1234ZE, or certainly transitioning to, you'll notice that the figures are somewhat similar to R32 with regard to RCLs at 4.7 versus 4.8, flammability levels that are close, a burning velocity, however, that is less. But again, neither of these A2L refrigerants are highly toxic nor toxic under the classification of Standard 34. So just a quick slide to give you a general comparison of the differentiation between 2 dominant refrigerants and variable refrigerant systems, R410A and R32. So what does ASHRAE Standard 15 have to say with regard to the designing of variable refrigerant systems using A2Ls. First of all, the forward of Standard 15 goes on to state that the standard incorporates more updates than any other edition in the standard's history, the 2022 edition. More updates than any other edition. So you can see that this is a very fluid, dynamic, expanding standard. And at any one time, it's hard to predict where the design, what design limitations are going to be incorporated in the future. So it's a little difficult. ASHRAE Standard 15, however, must be used in conjunction with ASHRAE Standard 34 because it relies on Standard 34 to provide the tested refrigerant characteristics that will be used for variable refrigerant systems in Standard 15. Again, the Standard 15 is directed specifically for the safety of persons and property, and its goal is to avoid stagnant pockets of refrigerant vapors within the occupied space of a building. And it goes on to state that be aware that leak refrigerant will always concentrate near the floor of a space because refrigerant is more dense than ambient air. The standard goes on to state in its purpose that it specifies safe design, construction, installation, and operation of refrigerant systems. And I just don't have time to go into maybe even 50% or more of what those specific design characteristics are. So I'm going to only be able to cover just the low-hanging fruit to give you an idea how the standard might be applied. The standard, let's have a look at that. But before we begin with this standard, let's review definitions and terms to be applied so that we have some sense of how these equations work and what they mean and how we can apply them. Standard 15 introduces effective dispersal volume, the volume of a space or connected spaces in which leaked refrigerant will disperse. It also uses the term effective dispersal volume charge, which is the maximum refrigerant charge permitted for an effective dispersal volume to fall within the refrigerant contamination limits called out in Standard 34. An understanding of lower flammability limit, which is the minimum concentration of a substance that is capable of propagating a flame through a homogeneous mixture of the substance. As it's the same definition as in Standard 34. What is makeup air? And this is an important term to understand. It is air added to a space from outside the building or from other indoor spaces by means of mechanical or natural ventilation. So makeup air in Standard 15 can be either outdoor air or even indoor air. It's not like ASHRAE Standard 62.1. Occupational exposure limits, we've already discussed. Refrigerant concentration limits is the refrigerant concentration limit determined in accordance with Standard 34 and intended to reduce the risk of acute toxicity, asphyxiation, and flammability. There's releasable refrigerant charge, and this is an important component in evaluating whether or not a VRV system meets the RCL limits in the smallest occupied space served by a VRV system. Releasable refrigerant charge is a portion of a system refrigerant charge that can be released into a space as a result of a single point of failure. In other words, one refrigerant circuit. Another term is a safety shutoff valve, an automatically controlled refrigerant valve for the purpose of limiting the amount of refrigerant released into a space when a refrigerant leak is detected. There's also system refrigerant charge, which is the total mass of refrigerant in an independent circuit of a system. And then there's the definition of a ventilated enclosure, a type of equipment enclosure that includes an integral ventilation system that will prevent refrigerant leaked inside the equipment enclosure from escaping into the space surrounding the equipment. Section 4 of Standard 15 has occupancy classification distinctions. And this does make a difference in how the releasable refrigerant charge is calculated. you will notice that institutions have 50% lower refrigerant contamination level than that prescribed for the refrigerant in standard 34. So if variable refrigerant is being designed for a school or a university or maybe even a hospital, we have to look into those refrigerant contamination limits to make sure that the institutional requirements are met. Section 5.1, refrigeration systems are actually defined. I only listed 3 here. I think there are about 6 or 7 in order to assign how that system might impact the design of a refrigerant system serving occupied spaces. And then there is section 5.2, which is a refrigeration system classification for the purpose of applying the data shown in ASHRAE 34, table 4-1 or 4-2, that classifies according to the degree of probability that a leakage of refrigerant will enter an occupancy classified area. So standard 15 says there are 2 classifications. There's a high probability system that is such that a leakage of refrigerant from a failed connection, seal, or component will enter the occupied space. And there's a low probability system in which the basic design is such that leakage of refrigerant from a failed connection, seal, or component cannot enter the occupied space. Refrigerant safety classification shall be assigned, again, in accordance with ASHRAE 34, and refrigerants with a refrigerant number designation in the reference standard 34 edition shall use the indicated toxicity classification and flammability classification for standard 15 application. Section 7 actually assigns a procedure and method for calculating volume of refrigerant that may be released into a space, of a volume of an A1 or an A2L refrigerant that can be released into a space. Effective dispersal volume is a term used throughout the standard. It is the cubic volume of space in the occupied space of a building or a room that is served by a variable refrigerant system. To expand the cubic volume of space, ASHRAE assigns a connected space level where natural ventilation can flow between connected spaces through vents and other listings as prescribed by the standard. Connected spaces, however, if they're going to be used to expand the effective dispersive volume of the occupied space, shall all be on the same floor. They cannot be interconnected through multiple floor levels. Permanent natural ventilation openings shall be sized in accordance with section 7.2.3.2.1 and 2.2. This is an important development. According to Ed Mendiata of Daikin, he goes on to say that the definition of what constitutes an airtight space is one of the most significant updates found in Standard 15. What can be defined as a connected space to increase the overall volume of the effective dispersal volume of a space. He goes on to say that the standard now provides the means of determining if 2 or more areas are connected, thereby increasing the effective room volume by establishing a minimum required natural ventilation opening. And here are the equations in the standard that shows how that minimum free area of opening is to be calculated. And this represents group A1 refrigerants. And notice that the assignment of that free area for group A1 refrigerants is a different equation from the assignment of group A2 refrigerants. So if you're designing to A2Ls, which you very likely are, remember that the free area of the openings that define a connected space have a different equation, and it's defined by section 7.2.3.2.2. So be aware of that. Section 7 goes on to provide refrigerant system charge limits. The effective dispersal volume charge shall be in accordance with this section of the standard. To calculate the effective dispersal volume charge, which will arrive at no more than the minimum RCL for an A2L refrigerant in the space. This gives you that maximum level of refrigerant concentration. This equation does. So it is the effective dispersal volume charge that is equal to the refrigerant contamination level times the effective dispersal volume of the space times the occupancy factor. Notice that F sub OCC is different for non-institutional buildings of being a factor of 1, and for institutional buildings, it is a factor of 0.5. So your RCL is halved for institutional applications of variable refrigerant systems using A2L refrigerants. Oh, and there's one other rather interesting note under 7.3.2 that the maximum total refrigerant charge of all refrigerant systems containing group A2 refrigerants or A3 refrigerants in occupied areas and machine rooms shall not exceed 550 pounds. So just be aware of that limit, and this information is embedded in the standard under these sections references. And by the way, I understand these presentations I give are very dense with specific detailed information, because I want this deck to be a resource for you to use in the future if you just wanted to have a quick check on something, because you're just not going to remember everything that I cover in this session. I'm probably not even going to remember it for that matter. But so please feel free going to Veritech's website into our training page and pull these sessions off so you have them as a resource for the future if you have any questions of what we covered today. Here's a very important term for defining how much refrigerant, A2L refrigerant, can serve an occupied space. It is the releasable refrigerant charge. And how do you determine that? Well, it's determined in compliance with the requirements of section 7.3.1, the effective dispersal volume charge, and shall be determined in accordance with sections 7.3.4.1 through 7.34.4.4. Releasable refrigerant charge determination will be in accordance with specification with these sections. And there's language that supports the design of single circuit refrigerants, which is the releasable refrigerant charge. That shall be the system refrigerant charge unless release mitigation controls are provided in accordance with section 7.3.4.4. There's language on multiple independent circuits that defines the releasable refrigerant charges shall be the refrigerant charges in each independent circuit unless release mitigation controls are provided. And then there's calculating releasable refrigerant charge, which with the release of mitigation controls complying with the standards, section 7 standard paragraph listed. So it's a lot of information. But let's look at calculation of refrigerant for an occupied space. So calculating releasable refrigerant charge is to provide the amount of refrigerant served by a refrigerant circuit released into an occupied space due to a single point of failure. So there may be multiple points served by a common condenser that can be isolated using safety shutoff valves in each independent circuit, which will lower the amount of refrigerant serving each space to allow them to more closely meet perhaps their RCL requirements per standard 34. So if we look at the M sub REL, or the releasable refrigerant charge, assures that the refrigerant released into an occupied space does not exceed a space's effective dispersal volume charge calculation. And that is a substantial component of standard 15 and being able to assess whether or not a design meets that effective dispersal volume charge calculated for space. So release mitigation controls are used to limit the releasable refrigeration charge within a space. Release mitigation systems shall have components that are UL 60335-2-40 compliance. They shall be permitted for reducing the releasable refrigerant charge on refrigeration systems where each indoor unit has a cooling capacity of 5 tons or less. And some ducted variable refrigerant indoor fan coils have greater tonnage capabilities. So just be aware of that. Release mitigation shall be activated by a refrigerant detection system. The use of refrigerant detection systems are now going to be used in the standard to help safety shutoff valves respond when there's a refrigerant leak and shutting off refrigerant circuits. So in the event of a failure of the release of mitigation controls or a refrigerant detector, the release mitigation controls shall isolate all possible paths of refrigerant that can leak into spaces. There's language also on location in a machinery room or outdoors for variable refrigerant systems. Should all components containing refrigerant be located either in a all components containing refrigerant for a variable refrigerant system shall be located either in a machinery room or outdoors where the quantity of refrigerant needed exceeds the limits defined in section 7.2. And this is untenable for VRV. It defies its purpose or whatever. So standard 15 lists design strategies to help overcome this requirement. There are also additional restrictions under section 7.5 regarding occupancies and flammable refrigerants not exceeding 1,100 pounds without an authority having jurisdiction for a building. There are additional restrictions for VRV systems that serve corridors and lobbies. Refrigeration systems shall be limited to unit systems. They will have its own assigned condenser. The refrigerant charge shall be limited based on refrigerant charge quantity. The refrigerant system containing A2L, A2, and A3 refrigerants shall be listed, and the refrigerant charge limited for each unit system calculated in accordance with equation 7-7A. So laying out a system for a corridor, you would use equation 7-7A to assign what that refrigerant quantity is serving that corridor. There are restrictions of refrigerant use in section 6 for refrigerants for human comfort. That is to say, high probability systems using A2L refrigerants for human comfort. Excuse me. So refrigerant quantity limits are the maximum refrigerant charge of any independent circuit for each refrigerant system as specified in section 7.6.1.1 and 1.2. Air circulation are variable refrigerant systems that have air circulation use a different equation from other system designs that do not have air circulation at the fan coil units. And be aware the manufacturer we represent does use air recirculation in all of its fan coil units indoors. 7.6.1 also allows for continuous air circulation or air circulation when there's a leak detected by a refrigerant detector. And here's the equation for other refrigerant systems that do not use air circulation strategies in order to reduce the RCL in the event of a leak. Group A2L refrigerants for human comfort also has language for mechanical ventilation, where a ventilated enclosure is provided to control a refrigerant leak. The refrigerant system and ventilated enclosure shall be listed to comply with this section. Because of the fans and the amount of CFM necessary to meet this 7.64 mechanical ventilation requirement, it becomes sort of impractical as to how to apply it in space. And the manufacturer we work with is moving in the direction of safety shutoff valves, isolating refrigerant circuits, and designing equipment to help meet the ventilation requirements at branch selector boxes and air circulation requirements at fan coil units. So every manufacturer, I'm sure, has their own way of dealing with the standard, but mechanical ventilation is certainly a method for controlling refrigerant concentrations in the event of a leakage. So let's look at a design of an A2L refrigerant for an office. First, let's look at the steps for laying this out. The first thing you need to do is lay out a system. The second thing you need to do is determine the space volume of each zone served by the system and understand what the smallest room is in its volume as the start point for what the maximum refrigerant concentration limit is in that actual system and how it's to be controlled. You then calculate the releasable refrigerant charge and then determine whether or not the releasable refrigerant charge meets or is less than the effective dispersal volume assigned to the space, or the effective dispersal volume charge assigned to the space. If it exceeds it, it does not comply. If it's less than, it does comply. And here's an example for an office building using safety shutoff valves at each of the branch selector boxes, serving one fan coil unit each. And we can see by that the condenser refrigerant, total pounds of refrigerant for the condensers used are listed at 48.79 and 36.08. And then to meet standard 15 compliance, the MREL calculation should be for the smallest enclosed space. Using a safety shutoff valve, we can now determine that the overall effective dispersal volume charge is calculated at 14.4. However, the releasable refrigerant charge of this specific example is 1.4 pounds, so it meets and conforms to the actual intent of standard 15. And here's a way of calculating a releasable refrigerant charge for grouped offices served by a common circuit. And if you run the math and calculations, you can see that by using shutoff safety valves, you can meet the refrigerant contamination limits as well. But this gives you an idea of how to run these calculations to see if whether or not your design is meeting conformance. So what does the International Mechanical Code have to say about variable refrigerant systems? And I'm going to go through this quickly as we're rapidly running out of time. I used IMC 2024 as a reference. It gives language on refrigerant piping installations that need to comply with ASME B31.5. It offers piping location directions regarding to compliance and which sections are to be applied. It looks at refrigerant pipe enclosures. Refrigerant piping shall be protected by locating it within the building elements or protective enclosures. It gives direction on where that piping is to be located, or whether it be indoors or outdoors. It also gives direction on refrigerant pipe shafts. Refrigerant piping that penetrates 2 or more floor or ceiling level assemblies shall be enclosed in a fire resistance rated shaft enclosure. The fire resistance rating that there's a typo. That the enclosure shall comply with section 72134 of the International Building Code. There's direction on location of pipes, and also in the use and design of A2L refrigerants, it gives shaft ventilation requirements that would be needed where you have refrigerant piping penetrating more than 2 levels. So be aware of that. That will now need to be incorporated into the architectural features of a building. And then there's refrigerant pipe installation requirements, such as naturally ventilated shafts shall have a pipe, duct, or conduit not less than 4 inches in diameter that connects to the lowest point of a shaft that extends to outdoors. Mechanical ventilation shall be continuously operated or activated by a refrigerant detector. Systems utilizing a refrigerant detector shall activate the mechanical ventilation at a maximum refrigerant concentration of 25% of the lower flammable limit of refrigerant, etc., etc. It also has language on stop valves or safety shutoff valves and how they're to be applied. And it has different language for refrigerant systems with more than 6.6 pounds of refrigerant, as well as, oh, I'm sorry, that's wrong. That should be for 100 pounds of refrigerant. It has a different language. That's a typo there. Anyway, apologize for that. That should be 1109.6.2 for 100 pounds of refrigerant. So one way to get around this is I would like to suggest is consider designing around 100% outside air variable refrigerant systems. Conventional variable refrigerant systems are designed with untempered outside air. At least that's what I've seen historically in our market, though we're starting to see a shift. These systems are designed for peak summer design load, and consequently condensers using VRV are frequently oversized that compromise their efficiency, as well as it increases the amount of refrigerant required to maintain the system. Be aware our greatest design day is in monsoon, not when it's 115 in June at a 72-degree wet bulb temperature. And if you have untempered outside air serving the fan coils of a variable refrigerant system, that fan coil is handling all the sensible and latent load. It's doing not only controlling thermal energy in a space, but also the amount of humidity in a space. So drain pans fill up with water, and consequently, these systems are rather inefficient. The problem is that we're at peak summer design load for very few hours out of the year. So these systems are designed to meet that, but at the rest of the year, they're not operating at the promise of their full efficiency levels. So sizing to peak demand loads results in higher mixed air temperatures at fan coils, greater cooling coil total loads, larger condensers, reduced turndown capability at the condensers because of their being oversized. Certainly when a building is in a part load conditions such as fall, winter, or spring, and the owner pays a higher operating cost and system efficiency is compromised. And these systems have to include design strategies in conformance to standard 15 that will handle the pounds of refrigerant necessary to serve these systems. So 100% outside air system that is decoupled from the variable refrigerant system is a good way to downsize the actual variable refrigerant component serving the occupied classification, the high probability classifications of standard 15. The concept is that you decouple the 100% outside air, you let the DOAS unit control building humidity by using lower dew point on the coil temperature and to actually provide effective control of the space. The result of by doing this is that you provide the outside air at load neutral condition to each independent zone, assuring that the prescribed outdoor air per standard 62.1 is actually reaching each zone. By handling the latent load and the load of the outside air at the DOAS that has an energy recovery component, you have lower cooling coil loads at the fan coil unit, lower condenser tonnage, improved condenser efficiency, smaller VRV footprint. And so this offers a lot of reasons to look at a decoupled 100% outside air solution. And to support this concept, I wrote a paper in 2022 for Engineered Systems magazine on 100% outside air systems. And we did an evaluation of 3 VRV systems with 3 different outside air conditions coming into the building. One was untempered outside air. One was design number 2 with a DOAS unit decoupled from the variable refrigerant system with 55 degrees off the cooling coil or a 53.3 degree dew point. And then we looked at a low dew point DOAS solution that provided 52 degrees off the coil or 48.8 degree dew point. And what did we find? We found that the total tonnage of these systems was significantly less than the untempered solution, which means the volume of refrigerant serving occupied zones is significantly reduced, allowing designers greater flexibility to apply A2L refrigerants if they use this design strategy. So you can see that if we use low dew point depression, there's a significant percentage of savings in overall tonnage, a significant savings on the amount of refrigerant serving these systems. Consequently, a designer will have greater flexibility in designing to A2L refrigerants. And not to mention, an owner has a day two advantage of greater energy efficiency by using a low dew point DOAS solution. So be aware of that. So looking at 100% outside air variable refrigerant, you have more efficient systems, better humidity control, and you have the VRF downsizing advantage to help systems meet the A2L requirements. So that's it for today's presentation. Sorry, I've gone a couple of minutes over. If you have any questions, please don't hesitate to ask, and I apologize for going over today.
All right, thank you, Dan. We don't currently have any questions in the chat. If anybody does want to put them in the chat, or you can come off mute and you can ask them. I see somebody's hand raised. You can ask if you'd like.
Hey, this is Xiao here, Dan. Can we go
Yes.
back to the office design example where we have that a group of office?
Yep. Okay, here we go.
Here we go. So that example right there, we have 4 indoor unit served by 1 safety shut-off valve, right?
Yes, that's a heat pump zone for for that large open area, correct?
And we're taking the releasable charge amount for the combination of the 4 indoor unit. Is that correct?
Correct.
So Dan, I had stepped out. I'm sorry. I'm not sure whether or not if I had fixed a little something here. Was this a question? Did you want me to jump in on this, or are you okay?
Well, I may ask you, Ed, but let's wait for the question. I think I know where he's going.
Okay, go for it.
So I think the assumption is if we have a single point break for the entire circuit, and all the refrigerant is going to leak into any of these space, correct?
Correct.
Let's see here. So I think the calculation is not on this page. Can you go to that page? Ah, here. Yeah.
No, you know what? I didn't have the calculation on this page because I knew I was running out of time with what I had. I just wanted to do a simple illustration. But Ed Mendieta, who actually ran the calculations and did give a sample, could probably speak to it if you wanted to ask him specifically.
Okay. That would be great because I saw like there are 3 numbers here: 1.41, 1.2, and 0.279. Is that it?
Just to let you know that it doesn't show which ones those are associated with. One is for the amount of refrigerant in the indoor unit. The other one is for the piping on the gas and liquid. And then the other one is a constant, which is the amount of refrigerant that passes through the valve during the time of, from the initiation of the event until the end of the event. That's a constant at the 0.279 pounds. And those are actually, calculated automatically within the selection software.
I see. So as an engineer, we're obligated to give you the area and volume, and the selection will do the safety calculation for us. Is that correct?
Yes, it will do the calculations for you. All you need to do is enter the amount of distance between that shutoff valve and the indoor unit. And as part of the selection process, I think that he had said that was step 1. You had already determined the size of that indoor unit. So with that information, the software can calculate that.
I see. All right. A separate question. Mixed use buildings. I understand we have ASHRAE 15. as a guideline for commercial application. There's a not a chapter, sister standard called ASHRAE Standard 15.2, and all the residential components shall
Correct.
comply with that. Do we have any other trainings on that sector by any chance?
Well, what we were thinking of to this point, in fact, Ed and I were talking yesterday, what we'd really like to do is have Ed present specific design strategies for laying out A2L refrigerant, variable refrigerant systems. And Ed would be the person who could support us in that effort and initiative. So we would love to set that up and provide that as a webinar Wednesday event.
All right, awesome. Thank you. Last question. The shelf enclosure requirement. There is a addendum for ASHRAE 15 coming out late May, I believe, 6 or 7 weeks ago. I think they kind of revised that.
That's addenda. It would be addenda A. You're talking about addenda A for 912 1.5?
Yes.
Yeah, so that one, and I'm sorry, we didn't have enough time to go over the latest slides here, Dan, but that one actually does not, a shaft enclosure is not required as a result of a recently published addenda A, and also a pending addenda B will make it so that if you choose to use a shaft, that ventilation will not be required for section 912 2.2.
Interesting. Okay.
My question.
One other thing, Dan, because I know that you had, this is just another part that I just didn't see that slide, but UL does allow indoor units up to 10 tons. And so there's another addenda, which is under review by ASHRAE, which will allow indoor units up to 10 tons.
Good to know.
Yep. So my question is, usually we don't take ASHRAE standard as code requirement until they're adopted by certain years of mechanical code. Do you know, or do you have any exposure to jurisdiction that basically telling you have to go with original ASHRAE Standard 15 2022 version? Because all those addendums is to 15-2024 version. So whether that's applicable or not, have you guys heard anything that, but being very literal to the law, we have to comply with the 22 version of ASHRAE 15. But the 2022 version of 15 is not written out very, let's say, perfect. So we have to reference a lot of the 24 version of the standard. Have you guys heard anything in that regard?
Dan, that's more regional, because I'm sorry, it's more of a micro regional because I cover the Western region. So I would not be aware of the regional requirements for AHJs as far as, what they're aligning with, if it's IMC, UMC, et cetera.
Okay. Good. Thank you, guys.
Thank you. All right.
Sure.
So we have a few more questions. So I'm going to go in order that I've received them: Jordan, Robert, and then Brandon. So Jordan, it's kind of a 3-part question here. Where will stop valves be added in VRV design by the manufacturer? Is it between the branch box and the fan coil?
From Daikin's standpoint, if you're talking about the location of where the safety shutoff valve is located, for heat recovery, that will be downstream of the existing EEVs in our BS boxes. So that will be between, what you would interpret as the current BS box and the indoor unit, if you're talking about the location of that valve. But it will be integral to the design of the BS box for heat recovery.
Okay. And what estimate does Daikin have for MREL roughly in, say, a 4-ton fan coil to a branch box at like 50 feet one-way length?
Well, that's pretty detailed. Based on just some of the example problems we've done, you're looking about anywhere between 1 and 2 pounds. But again, that's a big time guess on my part.
Right. And as designers, how can they estimate charge in the VRV system for the pipe volume contribution?
That would be done in the selection software, at least, from Daikin's standpoint, all that is done as part of the selection software process. As I had said earlier, you're just inputting the distance from the shutoff valve or the BS box to the indoor unit, and the indoor unit will already be, part of the initial design of that system. So you know what size that indoor unit is. With that information, the software will be able to calculate the rest
So that
for
is
the
something.
MREL.
So that's something, Jordan, that your outside sales person would be able to help you run through. All right, Robert, if you you have your hand raised.
Yeah, hey there, guys. So just a quick question is kind of following up on that same question about the stop valves. Is there any current guidance or thought process to adding safety shutoff valves like between the condensing unit and the box to basically isolate charges? So one of the ones that we've been running into is, even though the systems now are doing a good job of isolating that to a small enclosed space. Well, now it becomes a question of where the line set is run and where the branch selector box goes. And so a lot of times that box still needs to go in a relatively confined space. And so the problem is that the rest of the charge that's not isolated from the fan coils is able to still dump into that space, is it not?
Correct. And you're probably referring to outside of ASHRAE. These are UL requirements for enclosed spaces, manufactured components. Is that what you're
That's where
referring
I'm
to?
going with it. Yeah. So we've kind of seen some of that where it's like there's mixed guidance right now from different manufacturers, because obviously, number one, it doesn't have a refrigerant sensing device like a fan coil does to basically move air, right? So it's a static device instead. So you've got a problem there where now you have to rely on the RCL charge, not the LFL charge. So there's some issues and concerns there. But like in scenarios where you can't find a big open space to potentially install the branch selector box, like for example a hotel, where best to look at installing these to provide a code compliant design?
Well, actually, it's outside of your question, but there is an option that Daikin offers, which is an enclosure that does contain a refrigerant detector on it, and so that will basically address that particular scenario to where that is something that Daikin offers as an option in order to address that. The other question that you had was saying whether or not if anyone's ever looked at placing any type of a shutoff valve, or I think that's what you referred to it as, upstream of a BS box between that and the condenser. No, that's not something. I mean, I've heard of it, and I'm sure that it has been brought to the attention of Daikin, but whether or not if an actual solution has been provided for that, I have not seen one.
Okay. All right, thanks. I was just going to follow up on the other question too about the code review and stuff like that. So not only is the code, a static device, right, as far as how it's, memorialized and published, because they're not normally issuing addendum to the codes, but there's a misprint in the code about what the RCL charge is for some of the refrigerants, which is becoming a problem because it lists, I think it's 3.2 pounds, not 4.8 pounds. And additionally, they don't get into LFL. It's only RCL, which is not the way that ASHRAE reads it. So there's some differences there too.
Yeah, I believe if you're mentioning the ventilation opening and the reference to LFL, RCL, there was an errata that was put out to change that. I know that as opposed to addendas, they have erratas, but
No,
I don't know if it was in reference to.
Sorry, I'm talking about the mechanical code though, not ASHRAE.
Oh, okay. Then
yeah.
All right.
All right. I'm assuming you went back on mute, Robert, so you're good. Next, we have Brandon. He asked, how does addendum A to 15 and 34 affect EVC, EDVC calculations approach with a VRV system design?
Addenda A, the one that we just talked about for the shaft enclosures, and maybe I just need to if that person could just rephrase that if it is in reference to that?
Yeah, it's that is in addition to, you guys already touched on it a little bit, but the exempted spaces, it reads area
Right.
that contain only continuous refrigerant pipe or tube, including joints and connections that have been tested in accordance with section 9.13 are exempt from the effective dispersal volume calculation unless these areas are part of connected spaces per 7.2.3.2. So I was just
Right. So that
curious.
is,
Yeah,
oh, go ahead.
go ahead.
Go ahead.
I was just curious if, you know, with today's very thorough, thank you, Dan, explanation rundown of the CAFs. We've been obviously as mechanical engineers all dealing with this. I'm just curious how this plays into the calculations approach with VRV systems.
Actually, that addenda A really didn't affect our approach, or at least Daikins' approach in terms of, and I know there's a lot of different, I guess you can say, sub solutions that we're looking here. One is for ASHRAE, one is for UL. But really the one that changed some of our options was really based on an interpretation, recent interpretation to that was submitted by Mitsubishi last year. It took them a year to basically come back with a response, which was a no. But what that did is when that particular section that you had referred to for the exemption, it forced us to relook at that. And what our consensus, or at least Daikins' consensus on that, is that the manufactured components that they must be classified the same as the indoor unit serving a space. It's not obvious from that interpretation, but that's basically our approach. And so if you say if there was any type of a change, I guess it depends on whether or not if you've seen our design class or not. But really, it just goes back to using ASHRAE calculations for ventilated space opening, which really doesn't change much, except that opening can vary. And then also there was, at least earlier in this year, we were pointing toward an option with UL for ventilation as one of the options for the enclosed spaces where there's a manufactured component within an enclosed space. That is no longer, we're not saying that that's an option because it's based on ASHRAE equations, which we're saying are not practical. So really our solutions or the solutions that we'd offer go back to that enclosed ventilation, or that enclosure that we said, that I just mentioned to the last person that asked the question, that we do have that on-demand enclosure, or if you have sufficient volume in order to not exceed the RCL, or you can use that ventilation opening based on the ASHRAE equation. So those are the three.
All right. That answers my question. I think we're on the same page, just verifying that was the case. So appreciate it.
Okay.
All right. One more follow-up question from Jordan. Will the IOM for VRV have some rules of thumb on charge per foot?
I'm not sure what ILM is.
IOM, the installation and operation and maintenance guides.
I'm
So
sorry, can you?
the IOM, or even how Daikin has the little design guides where there's different
Right.
rules of thumb. Is Daikin going to release anything that would be about charge per foot to where they can have a rule of thumb?
Yeah, spot
without
on.
having
I would say that rules of thumb for this at this point are premature. I know that, and that's just from my experience and just working with different reps and questions, that they really are application specific. I know we'd like to see one, and I know we're going to be pushing for some type of flow chart that'll make it a little easier to understand. But we're going to have to let this settle in as far as if there are any other interpretations that come in terms of what we see as being practical solutions. We just want to keep the window open until the time that we do get a lot more projects in actually designed and out the door. But that's more of my opinion as to why we do not have rules of thumb at this particular point in time.
No, that makes sense. But in general, like, are we still just looking at pipe volume for the total length of piping to calculate that charge component?
Yeah, well, I'm not sure if you're familiar with what our software does currently. I do believe that it provides sufficient information in order to satisfy the requirements for your projects. Let's just say an HJ says they need to see room volumes or refrigerant calculations. You'll have that information. It's just a matter of how to convey that, in order to show that you're in compliance. And there's different ways of doing that. Unfortunately, right now, all we have is what we have on the report. And I want to say that, I believe that that's sufficient. But I've seen that depending on the project and depending on the information that they are requiring from you, you may have to modify that a bit. But the information is there.
Gotcha. Yeah, I think we don't have access to that selection software, so those rules of thumbs that were given previously and things of that nature just come in handy to us in the location of the box or something.
Jordan, you had one more question in here about, yes. You guys, you can go ahead and ask it.
Yeah, so when you're doing the calculations for, refrigerant charge limits, is ASHRAE Standard still saying we should look at both RCL and LFL, or does it default to one calculation only?
Well, EDVC is, I don't know if the word derivative is correct, but it is related to RCL. It's just that the EDVC is using the RCL as part of its equation. So they are related, but I don't know, Dan, if you want to expand upon that.
Isn't that equation 7.3? I'm looking for it now. There you go.
Yeah, for A2L, for A2, yeah, that was it.
Yeah. So yeah, the RCL is factored into what the maximum refrigerant charge level will be.
I thought that there was a separate calc for where it was the volume was derived from the LFL limit.
It depends on and I don't know if you recall just on my last response. Sometimes whoever you need to convey this information to show that you're in compliance can be in terms of volume or it could be in terms of quantity of refrigerant. So yes, you can go back and forth in terms of that volume because you see the volume is there. You just need to calculate for the volume. In that case, if you want to show compliance in terms of volumes, but you can use either. You can use either the quantity of refrigerant or the volumes.
And Jordan, it depends. This is the equation that you're referring to is listed for systems designed with air circulation. So if you notice that it uses LFL and not RCL.
Is that why it's using LFL and not the RCL? Because I kind of got the feeling it told us to ignore the RCL for A2L systems, where it kind of moved to an LFL based calc right there. Yeah, the one you got up on the screen. So otherwise, you got to kind of apply the A1 RCL calc, or if you're not the system with recirculation. Does that make sense, Dan?
I'm sorry, can you repeat that?
Like for R410A, right? You have to use the RCL calculation for standard 15. For A2Ls, it kind of moves you to this category, this new equation based off of LFL. Right. Does that mean that we can avoid the RCL calc for A2L refrigerants so long as we have systems with air circulation?
And my going through the standard, I did not see any language that would support that idea.
Right. So I think at the end of the day, my question really is, are you guys, when you're running through some example calcs, is the RCL still kind of your driving limiting factor just because the volume, went down so much per 1,000 feet?
Yeah, actually, I guess it's the way you're looking at these equations, because I know that Dan and I looked at these and I didn't realize that there's one for A1 and the other one for A2, that they're different equations. And so as far as the EDVC, that's the amount of refrigerant you're allowed into the space, which is the same thing as the way you're defining RCL. That you're saying there's a certain amount of refrigerant you're allowed into the space, and the other one is saying here's the amount of refrigerant you are releasing into the space, which is MREL. So I believe that we're talking about the same thing. It's just defined differently depending if you're looking A2 or A1. It's still a refrigerant concentration limit if you're looking at it in terms of the quantity of refrigerant.
But Ed, question, isn't it implicit in the RCL that the LFL has been taken into account based on the refrigerant classification? Yeah.
Well, yeah, you're looking at the refrigerant type. So if it's R32, you have 19.1. If you have a different refrigerant, that's going to be a different LFL. So unfortunately, I just don't have all of these variables in front of me, but I'm trying not to confuse the audience by saying that it's something different. We still are saying this is the amount of refrigerant that's allowed into the space, and you cannot exceed that. It's just that this is for the A2L. This looks different than the one for A1, which showed the RCL.
Hey,
yeah,
Ed.
Dan, you're right on my same question too.
Ed, sorry.
Yeah.
Can I interject real quick?
Sure.
Just to kind of clarify. Okay, so LFL is lower flammability limit. So that's going to be applied to A2L refrigerants, because it is slightly flammable. That's why we're using LFL. So in the past, we were using A1 refrigerant, and that was using RCL, right? So that had the 26 pounds per 1,000 cubic feet, RCL. So now that we're using LFL because of the flammability limits, right? We need to use that 4.8 pounds per 1,000 cubic feet. Does that make sense to everybody? Because it's because we're using A2Ls now, there's a flammability aspect to it.
Correct.
So it's kind of used interchangeably in a sense, because we have to take into account the flammability aspect of it.
Well, and that's exactly my question, Kelly, is it interchangeable, or are they two specific separate metrics and both calculations have to occur, one for toxicity control limit, RCL, and one for the LFL limit for flammability?
They're two separate things, because one takes into account flammability. The other one, because in an A1, it's not flammable. It's not even, so we had to create, basically A2Ls were created separately. It's a separate category because they were slightly flammable. So they're not full on A2s. That's why the L is there for the lower, the slightly flammable aspect of it.
Sure. I guess my biggest heartburn though is that, in 34 for R454B, we still list an RCL and an LFL for the A2L refrigerant. Compared to 410A, it went from 26 pounds or something like that down to like 3.4 or 4. That has nothing to do with the LFL. It's just that volumetric calc limit for toxicity or oxygen diffusion.
So Daikin has taken the proactive approach of putting, built-in SSOVs on the BS boxes, so that MREL calculation now can be. If you run a lot of, I've done a lot of selections, and the pounds per 1,000 cubic feet that it actually you exceed it, you comply by a lot.
Yeah,
you're not gonna. Yeah. So you're not taking the whole
system would probably have more charge released to the zone as opposed to VRV with stop valves.
Correct.
Okay.
Because you have to take in a heat pump system, if you don't have any SSOVs, you have to take into account the whole entire charge of the system.
Does anyone know how the SSOVs are controlled, or what happens if they're like electrified and you lose power?
I think we have bigger problems than we lose.
I couldn't tell you the specifics of that because we don't have the full documentation on those. So I'd hate to give you the, incorrect information.
I'm done, I promise. Thank you.
What I'm hearing is that we definitely need more of this. So,
Absolutely.
yeah, in our newsletter, I had sent out, there was a poll question that asked if anybody would be interested in an ASHRAE 15 specific session, like a bigger seminar, multiple hours, or maybe something deeper diving this and all these equations. So it sounds like this topic is something that we definitely need a lot more time on. Am I correct in that statement?
At 1 hour sessions
Yeah.
are less than adequate in
Yeah,
order
okay.
to provide a more comprehensive
All right. So,
awareness of what the standard is calling for.
okay, perfect. We'll figure out how that looks, if it's something that we do on a webinar, to where we can get all of our offices, all at once, or if it looks like something that would be better done in person, in each of the locations. If anybody has a strong opinion one way or the other, I'd love to, share your opinions with me, email or whatever in the chat, and we can get something going to deeper dive this topic.
Absolutely. There certainly is a need. And
Yes.
again, the standard is continually unfolding, as Ed mentioned earlier. I mean, the addendum after addendum after addendum. It's just very difficult.
Yeah. So I think, if everybody agrees, I've gotten through the list of questions, and I would love to look into a deeper session on this soon, if everybody is good with that.
I think it's a great idea, considering this is the longest
Yeah.
list of questions we've had under any presentation. In fact,
Yes.
I'm sorry to say I've got to leave. I've got a 2:00 appointment.
Yeah, same. So, let's go ahead and wrap up Wednesday's webinar, and we'll send out more information about something more in depth here soon. So thank you, Dan. Thank you, everybody that is still on, for spending 30 minutes with us to go over questions. And we look forward to seeing you in September for our webinar. Dan?
Thank you very much, all of you, for joining us today. I'm glad to see there was so much engagement. Let's see what we can do to expand the conversation.
Perfect. Thank you, guys.
Thank you.
Thanks very much.
Bye.
Thanks.